Assalamu alaikum, everyone. Welcome back to this discussion on steady state, steady flow devices. So today we're going to continue our discussion on these devices and basically introduce two more devices. One is throttling valve and the other would be effectively the heat exchangers. Okay, so just like what we have done before, we'll start with applying some sort of a general energy balance, talk about what makes sense, and then come up with the specific energy balance for each of these devices. Okay, so that's roughly the plan. And once we have done that, of course, we will go ahead and solve some problems for these kind of situations. Okay, so let's start with the throttling valve. Now, a throttling valve is simply a kind of a flow restricting device, right? It restricts the flow. And the whole purpose of trying to restrict the flow or say slow down the flow is to basically create a huge pressure drop in the fluid. So the reason why we make use of a throttling valve is because we want to achieve a certain pressure drop, a relatively large pressure drop. Okay, now why do you want to achieve a pressure drop? We'll talk about that in a bit. But for now, remember that we use throttling valve whenever we want to whenever we want to achieve a given pressure drop in the fluid. Now you may ask that, we can achieve a pressure drop even in a turbine. So why make use of a throttling valve? Well, there are situations where all we are interested in is to achieve a pressure drop and um, related to that, a temperature drop. So in such situations, we may not be interested in producing the given amount of energy or the power output, right? Like what you do in a turbine. In a turbine, you expand a given gas or a fluid, and then it produces power output while at the same time undergoing a pressure drop. Whereas when we talk about the throttling valve, there is no work output. Okay, all it does is reduce a pressure drop, and it does so in a very say stable, in a very sustainable and a robust manner, and it's a really small device. So if you want something that where you know that the power output is going to be really small and where your main purpose is to actually reduce the temperature and not actually create power output, then you use a throttling valve. A very common application where this is a situation is the case of a refrigeration or an air conditioning system. In each of these systems, whether we're talking about the refrigeration or air conditioning systems, we need to decrease the pressure of the refrigerant from the condenser pressure to the evaporator pressure. Okay, we have not talked about all of that, but for now, just remember that we need to reduce the pressure drastically. We need a significant pressure drop, and we don't really care about work output, right? Refrigerators and air conditioners, they consume power to give us the cooling that we need. So in this case, what we do is we make use of a throttling valve because what we are interested in ultimately is a huge drop in temperature. And this can be achieved for the refrigerant if we decrease its pressure. And that is what we do by making use of a throttling valve. Now remember, not every fluid will undergo a reduction in temperature if you drop the pressure. So what I'm saying is if delta P is negative, right, then it is not necessary that delta T or the change in temperature will also be negative. Meaning if you decrease the pressure, there is no guarantee that the temperature will also decrease. Therefore, in all these applications, you need to use a specific type of a fluid where you are sure that if you decrease the pressure, then temperature will also decrease. We'll see a couple of cases where actually this will not be true, and therefore we cannot use such substances as the refrigerants or the working fluids in your refrigerator or air conditioning systems. Okay. Now this is a very simple schematic to show you how how throttling valve looks like. It could be some sort of a valve like this where we are just putting a restriction here to restrict the flow and create a pressure drop. Or it could be some sort of a porous duct, which is basically a cylindrical device with a lot of tiny holes. So basically the fluid, if it has to go from state 1 to state 2, then it has to go through these really tiny holes, and you're sort of putting an obstacle in the flow, right? So you're restricting the flow, which of course causes the pressure drop. So P2 is going to be smaller than P1. And in most cases, we select a refrigerant or we select the working fluid in such a way that T2 is also smaller than T1. But as I said before, this is no guarantee. So you need to select a proper substance as well to make use of it in a throttling valve. Okay. Now, when we talk about the energy balance, right? So let's just write down the energy balance. It's a steady state, steady flow device. So the energy that's coming in should be equal to the energy that's going out. In general, you can write it as heat in plus work input plus summation m dot n times enthalpy inlet plus kinetic and potential energy. Same way, it's equal to q dot out plus work output plus m dot out times enthalpy at the outlet plus kinetic and potential energy. We know that the changes in kinetic and potential energy are negligible, right? So I did not even bother writing them. And that's the situation in most cases, except a nozzle and a diffuser. And this is something that we take always, almost always. So you don't even have to bother about writing the kinetic and potential energy terms for a throttling valve. Now, in a throttling valve, as you can see here, the fluid is just entering and it's going out, right? There is no work input. There is no work output. It is not designed to produce any work input or output. And also the fluid goes through so quickly that there's no chance for even heat transfer to happen. So there's no heat coming in, there's no heat going out. So the only thing that's happening is you have certain amount of mass coming in with some enthalpy, and exactly the same mass goes out with the same enthalpy. So since throttling valves are mostly single inlet, single exit devices, meaning one inlet, one exit. So I can write this as m dot n hn is equal to m dot out h out. And I know that the mass that's coming in has to go out, right? It's a steady state, steady flow system. So m dot n is equal to m dot out, and I can cancel them both. So basically, I'm saying what I'm saying is hn is equal to h out. Enthalpy at the inlet is almost equal to enthalpy at the exit. And that is the simplified energy balance for a throttling valve, right? So you can always remember that when you talk about a throttling valve, you should know that the enthalpy is constant, or it's an isenthalpic device, or the fluid undergoes an isenthalpic process in a throttling valve. Okay, so I'm not going to tell you that the enthalpy at the inlet is equal to enthalpy at the exit for a throttling valve. By this understanding that by the understanding of what a throttling valve does, you should know that this is what it is, and you should be able to use this formula in examples or while solving examples. Okay, so when we say enthalpies are same, we are not trying to say that everything is the same, right? Only the enthalpies are same. Now, if I can break down the enthalpy, I can break down H1 into U1 plus P1 V1, right? Because H is equal to U plus PV, and H2 is U2 plus P2 V2. So if you think about it, if you look at a porous plug or a throttling valve, one example of a throttling valve here, the enthalpies are same. Enthalpy at the inlet is equal to enthalpy at the exit, but we can have variations in internal energies at the inlet and the exit, right? So in this particular case, we see that U1 is greater than U2, okay? But at the same time, the other term, P2V2, is actually much smaller. Sorry, it's much greater than P1V1, right? So basically, if U1 is greater than U2, then of course P2V2 should be greater than P1V1, so that it compensates for the summation of the thing, right? Because enthalpy is same. So basically what we are saying is enthalpy has to remain constant, but internal energy and flow energies, they can be exchanged, right? They can be converted from one form to another. So here at the inlet, we have a relatively small flow energy. At the exit, we have relatively high flow energy, okay? But the internal energy is smaller. So you can have changes in internal energy, that is feasible. We cannot say that U1 is equal to U2. No, this is not true for a throttling valve. The only thing we can say for a throttling valve is H1 is equal to H2, or enthalpy at the inlet is exactly equal to the enthalpy at the exit. Now, when we talk about enthalpies, we need to remember that this is not going to be the same for all fluids, right? For any fluid undergoing a throttling process, H1 is equal to H2. Okay, it's true for all fluids. However, when this enthalpy is remaining constant, it does not mean that we cannot say that T2 is going to be smaller than T1, or we cannot say that if P2 is smaller than P1, then surely T2 is going to be smaller than T1. We cannot. This does not apply. This is not true always. Okay. So let us look at an example where it is not true. So if you consider an ideal gas, we know that for ideal gases, properties such as enthalpy, internal energy, they depend only on temperature. All right. Or if you fix the enthalpy, then the temperature is also going to remain a constant. In such cases, if you're dealing with an ideal gas undergoing a throttling process, then since enthalpy at the exit is exactly equal to enthalpy at the inlet, it basically also means that the temperature is going to remain exactly the same. So therefore, although we are having a pressure drop, although P2 is smaller than P1, T2 is exactly equal to T1. T2 is not smaller than T1. So this is one very clear example where reduction in pressure does not lead to a reduction in temperature. Okay, so therefore you got to make sure that you make use of an appropriate fluid when you're using them in refrigeration and air conditioning applications. Otherwise, if you have to use a throttling valve with an ideal gas, you should know that both temperatures and enthalpies are going to remain the same, because for any throttling valve, this remains absolutely true. The enthalpy at the inlet should be equal to enthalpy at the exit. Okay, there are a couple of solved examples in the textbook. Please go through it for you for better understanding or for understanding how to make use of this. Okay, it's a very simple concept. I'll not be solving problems on throttling valve. So now let's move on to the other devices, which is one of which is a mixing chamber. Okay, mixing chamber can also be thought of as a direct contact heat exchanger. Okay, so what the reason I say direct contact is because both the hot and the cold fluid, or both fluids, they sort of get in touch directly. Okay, so what does a mixing chamber look like? Well, it looks like the one shown in the figure. You can have you typically have two inlets, one exit, or one inlet, two exits, right? So here we have an example where you have one inlet, sorry, two inlets and one exit. So it's basically a chamber where things get mixed. Okay, so that's where the name comes, right? This is something very similar to what happens in the shower. Okay, when you try to mix hot and cold water, or what happens in your tap when you try to mix hot and cold water. So you have two inlets, one for hot water, one for cold water, and ultimately one outlet, which is the tap, where you're getting the temperature exactly at what you want. All right. So when we talk about mixing chambers as well, we can start with the general energy balance. And we know that in a mixing chamber, its role is not to produce any heat. It does not take any heat input at zero. Of course, there's no work happening. All right. Work in and out both are zero. In general, the heat output is also zero. There's no heat loss to the surroundings because this device is really, really small. So there's no chance, there's not much space for heat transfer to occur in most cases to the surroundings. The changes in kinetic and potential energy are negligible, right? So we can cancel out. They are not zero, but they cancel out from inlet and exit. So what you're again left with is very simple. M dot n, summation of m dot n hn is equal to summation of m dot out hn. Okay. So how would that look for this particular device that we have shown here? So let's say this is inlet one, this is inlet two, and you have outlet three. When I say the summation of m dot in hn is equal to summation of m dot out h out, what I'm saying is the product of mass flow rate at the inlet times enthalpy for as many inlets as you have should be equal to the product of mass flow rate at the outlet times enthalpy of the outlet for as many outlets as you have. Here in this particular example, we have two inlet, one outlet. Okay, so here I can write it as m dot one h1, which is in inlet one, plus mass flow rate at state at inlet two times enthalpy at inlet two or state two. This is going to be equal to the enthalpy times mass flow rate that goes out at the exit, which is simply m dot 3 h3. So this is simply what you get by applying energy balance to this. Okay, as simple as that. If there's any heat, also if there's some heat being rejected from this control volume to the surroundings, then you can also add plus q dot out. Okay, in general, this is not the case. This is generally zero. So this is how the energy balance would look like. Okay, so again, you can look through problems on how to solve it, right? But this is a very simple energy balance that we can make use of it for solving for a mixing chamber. There's another example here. Another example which is very common around us. So if you consider the air conditioning systems and in huge buildings or in malls, for example, or even in your car, right? So there is basically some amount of outside air that's mixed with return air. And what you get is the mixed air that comes out of the air conditioning system. Okay, so this is again a situation of two inlet and one exit system. And you can, write down a similar energy balance for this, just for your own purpose, and make sure you understand how to do that. Okay, it's gonna be same as what we did here at the top. All right. So this is our mixing chamber. Now we also have other heat exchangers where the two fluids do not mix. In general, when we say heat exchangers, we're talking about devices where you have two fluids. It can be liquid or a gas, which exchange heat without mixing. In generally, this is how we can call it, right? Where you have direct mixing, then you call it as a mixing chamber, which you can call as a heat exchanger, but it's okay. So in this case, also when we look at let's say a kind of flow heat exchanger where you have two fluids, coming from opposite directions. So this is inlet for one fluid, and this is the another inlet here. You have the two fluids coming in at opposite directions, right? And then the flow is opposite to each other, which is basically, as the name suggests, counter flow. Uh, for this heat exchanger or a cross flow heat exchanger, where the flow is perpendicular to each other, flow of the two streams, we can again start off with a very similar energy balance that we did for the mixing chamber and end up with the same expression. In general, a heat exchanger is not supposed to reject, it's not designed to reject heat to the surroundings. Q out in general is zero, but it can be non-zero in some cases. Okay. And it would appear on the right hand side along with m dot out h out. Otherwise, this is how the energy balance formula would look like. We have an example here for heat exchangers, so I'll show you how to make use of it. Okay. Now, one way of dealing with a heat exchanger, like the way we wrote down this energy balance, is when we treat the entire heat exchanger as one control volume, like shown here, right? The entire heat exchanger, we are treating it as a control volume. So whatever heat exchange is happening inside. All right. Now, alternate scenarios could include where you have some heat loss or heat gain from the surroundings, and you got to take that into account. Okay. So if it's Q in, then you write it in on the left hand side. If it's Q out, you write that term on the right hand side. There may be situations, not very common, but there are situations where that happens. Another situation could be that you don't consider the entire heat exchanger as the control volume, but rather you just consider one tube as a control volume. So instead of taking the entire heat exchanger, I just take maybe this tube, okay, and I draw a control volume around it, and then apply energy balance on this control volume. Now, if I treat this tube as a control volume, of course, there's heat loss or heat gain from this tube to the surroundings. Okay, so let's say there's Q out that's happening, then I got to put that in the energy balance when I write it for this tube. Okay, so the energy balance is going to be different in that scenario. Of course, there's no work output or work input, but there can be some heat output or heat input, depending on what sort of situation that you're dealing with. Okay. Now, when we talk about heat exchangers, we normally do not call them as a heat exchanger, but we have names depending on what they are supposed to do or what their role is in any given device, right? So basically, when we talk about heat exchangers, some common names given for heat exchangers are boilers, condensers, evaporators. All of these are heat exchangers, right? All of these devices uh, exchange heat between two fluids, and basically they come in different shapes and sizes, but you can apply this sort of energy balance equation in general to solve for them, or you could have situations where you got to take into account the heat loss or gain in some scenarios. Okay, so I'll show you how this alternate scenario one works. I'll show you how this alternate scenario two works. And we have already discussed how we'll deal with alternate scenario one. And I'll show you how to use both methods, meaning first method, which is treating the entire heat exchanger as a control volume and solving for it, or just treating one of the tubes as the control volume and solving for it. Okay, we'll show you how this works through an example, which we'll be doing next. So now let's talk about this rather simple example on a counterflow heat exchanger. Okay, so here what we are dealing with is a thin-walled double pipe counterflow heat exchanger. So we have a counterflow heat exchanger, okay, like the one shown in the figure here. Uh, you have one inlet here, one inlet at the top. Of course, the hot oil is going left and this cold water is going right. Okay, so they are in opposite direction in terms of the flow. So it's a counterflow heat exchanger. Okay, and we have this kind of flow heat exchanger, and we are using it to cool the oil. The specific heat for oil is given. Okay, and remember, whenever the specific heat for a substance is given, you're supposed to assume constant specific heat. All right, because you have been already provided with it. You have been already provided with a number. Okay, so you're using you have a counterflow heat exchanger, and the whole purpose why we purchased this counterflow heat exchanger or designed it is because we want to cool the oil from 150 degrees Celsius to 40 degrees Celsius at a rate of 2 kilogram per second. Okay, so the mass flow rate of oil is given. We know the temperature at which it enters, and we know the temperature at which it exits, or the temperature at which we want it to exit. And how are we cooling this oil? Well, we're using water with given CP, right? CP for water, and we're using water to cool it down. And the water, of course, enters at 22 degrees Celsius and it flows with a mass flow rate of 1.5 kilogram per second. So we know the inlet temperature for water. We know the inlet mass flow rate for water. We do not know at what temperature it is exiting. Of course, it is cooling down the hot oil. So the temperature at the exit for water should be greater than 22 degrees Celsius. This is simple understanding of the problem, right? This is something that you should expect. What we need to do here in this particular case is we need to determine what is the rate of heat transfer that's happening in the heat exchanger. So we're talking about what is the amount of heat that is getting transferred from the hot oil to the cold water. Okay, what is Q dot? And also we need to determine the exit temperature water. So how hot is the water when it exits from the heat exchanger? Okay, so these are the two things that we are looking out for. And the system that we are dealing with is again an open system because there's mass coming in and going out. We have oil and water, the two fluids that we're going to deal with, and we have been provided the specific heats. And we know that there is one inlet and one outlet for each one of these two fluids. So hot oil enters in one inlet, goes out from one outlet. Same way, cold water enters from one inlet, goes out from another outlet. Okay. So let's write down the conditions provided to us. Oil inlet temperature, water inlet temperature, oil mass flow rate, water mass flow rate. And then at the exit, the oil outlet temperature. We know that the mass flow rate water for the inlet is mass flow rate of water at the inlet is exactly equal to mass flow rate of water at the exit. So you just write m dot w. Same way for oil because you have one inlet, one exit systems, and these are all steady state, steady flow devices. Okay, so there's no chance of water or oil accumulating within the system. What comes in has to go out. And we have not been told there is any heat loss from this heat exchanger to the surroundings, right? Q dot from this heat exchanger as a whole. It is not losing any heat or gaining any heat to the surroundings. So you can say it's an adiabatic device, right? And this is what we normally assume. This is the default assumption. If nothing is provided about heat loss from the heat exchanger to the surroundings, then you just take it as zero. You treat it as adiabatic. So now, based on this information, we need to, determine the heat transfer and the exit temperature for water. Now, there are two ways to solve it. We'll talk about the first way first, and then I'll show you an alternate solution. So in solution one, what we will go ahead is what we will assume. So in solution one, we will take the oil tube, right, as a control volume. So this is the tube that's for the oil, and we'll just treat it as one control volume. And if you take oil tube as a control volume, well, of course, it's just a tube. So it's again a steady state, steady flow device. The energy coming in should be equal to the energy going out. But at the same time, when we consider the oil tube, right, the tube for the oil, we know that there's some heat transfer happening from the oil tube to the cold water. So there's heat being rejected from the oil to the water. So in this case, we can simply write it as the mass flow rate of the oil times its enthalpy at the inlet should be equal to the mass flow rate of the oil times its enthalpy at the exit plus Q dot out. Okay, this is simply from the energy balance equation that we have been talking about before, because we always treat changes in kinetic and potential energy to be zero in all such cases. So here what we want to determine is Q dot out. How much heat is being transferred from the oil to the water? Okay, so Q dot out is simply mass flow rate of the oil times the change in the enthalpy. How much enthalpy is reduced between inlet to exit, right? Since we have been provided the specific heat for oil, we are going to treat it as a fluid with constant specific heat, which basically means that we can substitute delta H as Cp delta T. And that's what we do here. So instead of delta H, we write it as Cp of oil times delta T for oil, temperature of oil at the inlet minus temperature of oil at the exit. Okay. So we have the mass flow rate of oil given to us, Cp of oil is given to us, and of course the temperatures are also provided. So now we can just plug in those numbers. Okay. 2 kilogram per second times 2.2 kilojoule per kilogram degree Celsius or kilojoule per kilogram Kelvin times 150 minus 40 inlet minus exit temperature for oil, and what you get is 484 kilowatt. This is the amount of heat that is getting transferred from the oil to the water. Okay, heat transferred from oil to water. So this is one thing that we wanted to determine in the problem. All right. We also need to determine the exit temperature for water. So now let's treat the tube for water as another control volume. All right. So let's do it here. So now water tube is the other control volume, and of course there's some amount of mass coming in with some enthalpy at the inlet. Same way mass going out, the same mass going out with uh, higher enthalpy at the exit, and there is some heat coming into the system from the heat lost by the oil. Okay, so energy in is equal to energy out, and we have heat coming into the system from the hot oil plus m dot w times HWI, which is simply mass times the enthalpy at the inlet, should be equal to mass times the enthalpy at the exit forward. Okay, so I can rearrange it to write it in terms of Q dot N is equal to m dot w times enthalpy of water at the exit minus enthalpy of water at the inlet. Again, when we are looking at delta H for substances with constant specific heats, we can write delta H as Cp delta T, and we are able to do that because Cp is provided, right? Either Cp should be given in the question, or the question should mention that you can treat the fluid as something with constant specific heat. Okay, so here you can write it as m dot w Cpw delta T. All right. What we want to determine here is temperature of water at the exit. So we can rearrange this equation to write it in the form of knowns and unknowns. So everything on the right hand side is known. Temperature of water at the inlet is known. The amount of heat that's coming into the system is known because it's exactly equal to the amount of heat that came out from the oil that was transferred or rejected from the oil. Okay, mass flow rate of water is known. Cp is given in the question. So again, there's no heat loss to the surroundings. So the heat that is lost by oil is only gained by water. There's no other thing that no other quantity that's transferring heat. So therefore, we can just write Qn. We can start substituting the numbers in here. So this is 22 degrees Celsius plus 484, which is the heat input into the water by 1.5 the mass flow rate of water times 4.18. Okay, so when you do the math, this comes out to be 99.2 degrees Celsius. So this is the exit temperature, and this is the amount of heat transfer. Okay, so this is one way of dealing with this, solving this problem, where we treated both tubes of the heat exchanger as control volume. So we solve them one by one. All right. Now, an alternate solution is to treat the entire heat exchanger as one control volume. So this entire thing, I treat it as one control volume. Okay. And if I treat the entire thing as one control volume, I can say that m dot n Hn from all different for all different fluids should be equal to m dot out H out for all different fluids. Okay. Now I can write it down in terms of water and oil. So mass flow rate of oil times enthalpy of oil at the inlet plus mass flow rate of water times enthalpy of water at the inlet should be exactly equal to mass flow rate of oil times enthalpy of oil at the exit plus mass flow rate of water times enthalpy of water at the exit. Okay, so whatever comes in has to go out in terms of the energy. That's all what we're saying. Now here I'll rearrange it to make it oil on one side. So m dot mass flow rate of oil times enthalpy of oil at the inlet minus enthalpy of oil at the exit should be equal to mass flow rate of water times enthalpy of water at the exit minus enthalpy of water at the inlet. Okay, now this quantity right here is talking about the energy that's lost by the oil, right? Q dot out from the oil is exactly equal to the amount of heat that enters the water. Okay, so the quantity m dot O times mass flow rate of oil times the change in enthalpy of the oil is the heat transfer that we're looking out for. And that's so we can calculate this quantity right here, and we get 484, just like we got from the top. Now, to get the quantity, to get the exit temperature, we simply need to use the fact that mass flow rate of water times Cp water times temperature of the water at the exit minus temperature of water at the inlet is exactly equal to the same quantity of heat that was lost from the oil, which is 484 kilowatt. Okay, which is exactly similar to what we have done there in the previous case. So here we know everything except the water temperature at the exit. So we can solve for the water temperature and it should come out to be 99.2 degrees Celsius. Okay, so again, this is different way of solving for it, but if you understand what the different terms are in the energy balance, you can solve it in this way as well. So this is alternate solution 2. You can use any solution as long as you know what you're talking about and as long as you can um, show the correct understanding in solving this problem. Okay, so as long as you do that, any of these solution will give you full marks. All right, so now let's move on and talk a little bit more about other sort of devices. So we have covered almost all the steady state, steady flow devices that are very common across different applications. Okay. In addition to that, you can also deal with situations where we're talking about pipe and duct flow, right, which is very common in the industry and also at home. So you have a lot of ducts or pipes carrying different fluids, right? Water, air, and so on. So whenever we deal with the transport of fluids, it generally satisfies the steady state, steady flow conditions, which means that the energy balance that we spoke about applies, which is energy at the inlet should be equal to the energy at the exit. Now, here I'm just talking about a couple more situations where, in addition to the mass coming in and mass going out, you can also have a situation where you can have electrical work that's coming in or different form of work that comes in, right? So, for example, if you look at the situation here, we are using an electrical coil to heat up the fluid that is entering the tube or the duct. All right. So, in such cases, the energy balance will change just a bit. Okay. We also have a lot of situations where there is heat loss from the hot fluid that's flowing through a pipe or a duct to a cooler environment. Okay, this is also a this is also a relatively common situation, and it'll again change the energy balance a bit. We have discussed about how it will change in the previous case for heat exchanger. It will exactly change in the same way for a duct as well. Okay, so let's look at these two situations through an example. If you're dealing with a duct here, like shown, okay, so there's air coming in at some volume flow rate, going out at another volume flow rate. Okay, there is heat loss to the surroundings that is happening, and also there's some electrical work input which is being used to heat up the air. So of course, if you're heating it up, then T2 should be greater than T1. Okay, otherwise you don't need this sort of a duct system. So in this case, where you have heat electrical work coming in and heat going out of the system, the energy balance will change just a bit. Of course, you start with energy N is equal to energy out. But in addition to the energy coming in through the mass times enthalpy of the system, you also have some energy coming in through the electrical work input, which is what you need to write on the left-hand side. Same way on the right-hand side, in terms of the what's going out, you have, of course, the energy going out in the form of mass times the enthalpy, but we also have energy being rejected in the form of heat, right? So you just have to take into account these two situations. And of course, if you're talking about a gas or any substance with the constant specific heat, then you can replace delta H with Cp delta T as we have done before. So this is another sort of situation that you can come across. Okay, so this is all about steady state, steady flow devices. Now let's just talk for a minute about how do you integrate these devices, right? So now when we talk about different devices such as nozzle, diffuser, turbine, compressor, throttle valve, mixing chambers, heat exchangers, pipe or duct, these are all very different devices which are designed to give us a specific thing, right? They're designed to achieve a certain objective. Okay, a nozzle is used to increase the velocity or decrease the pressure. Diffuser does the opposite. It increases the pressure at the cost of velocity. A turbine is used to give us a work output. Pump is used to increase the pressure, or a compressor is used to increase the pressure. Throttle valve is used to decrease the pressure and also the temperature At the same time, it's an isenthalpic device. Mixing chamber, you use it for mixing two fluids. Heat exchanger, the same thing. And pipe and duct, you transport fluids in this. Okay, so each of this device has a certain role to play. Okay, and the way we can combine all of these devices is by being more creative. And the idea is you should be able to combine all of these different devices that we spoke about in ways that help you achieve the overall objective. Okay, so of course, as an engineer, your role is to keep the cost minimum, but you got to make use of all of these devices to see what you can achieve, right? Each device can give you something, so you got to combine them in a way that makes sense. Okay, so I'll give you an example in a bit, but let me put that in another way. Another way of dealing with this thing is to say that, all these things that we spoke about, nozzles, diffusers, turbines, and all that, those are like the Lego blocks. Okay, so each block has a role to play, right? Now, you combine the blocks in differently depending on what kind of system you're trying to build. If you want to build a house, then of course you got to combine these colored blocks in such a way that you get your overall objective. But you're just combining these individual blocks, right? Same way, if you want to build a car, a red sports car, then you combine all of these blocks in a different way, and you probably get some more components to get you this car, which is again made up of Lego blocks. Okay, so the idea, what I'm trying to tell you is, as engineers, you got to think as at nozzle, diffusers, turbine, and all of these devices as Lego blocks, which you can combine in different ways to achieve a certain objective. Okay, so let's look at how we can make use of this different engineering Lego blocks to achieve the objective of a power plant. So for example, if you're trying to design a power plant, and we'll talk about this power plant thing in a little bit more detail later, but if you're trying to design a power plant, the whole purpose of building a power plant is because, well, you got to produce some work output. So if you want to produce some work output, right, if you want to produce some power for running, for providing electricity and so on, we know that we need a turbine. Yeah, the turbine is really essential for giving us that. And we know that a turbine takes usually very hot gases or hot fluids at the inlet, right? So if you're dealing with a steam power plant or something like that, then you need something that can heat up the steam. Okay, so you need a heat exchanger that heats up the steam. So that's what is called a boiler, right? So this is another heat exchanger, just a heat exchanger, and you can apply the energy balance equation that we spoke for this heat exchanger. Now, so you send in a hot fluid, you heat up the fluid within the boiler, send it to the turbine, it expands, produces the work output, comes out at relatively low pressure and low temperature. Okay, but we want to reuse this fluid. So typically, if it's water, you want to reuse it. So what you do is you bring it back to some sort of an initial state, right? So you let it go through a condenser, which is another heat exchanger, right? Where it rejects heat to the where it rejects heat to the environment. Okay, so that's Q dot out going to the environment, and then now you are at low pressure and again relatively low temperature. The reason you use a condenser is simple because at the exit of the turbine, you're having, in most cases, you are having a saturation mixture. But a pump cannot take a saturation mixture. You need, for a pump, you need something that's either compressed liquid, or in the worst case scenario, it needs to be saturated liquid. It cannot be a mixture. So to convert a mixture into saturated liquid or compressed liquid, you have to reject more heat, and you do that in a heat exchanger, which is called a condenser. Once you do that, then you are at the pressure and the temperature and in the phase that you want, which is the liquid phase. And at this point, we can send it through a pump. Why do we want to send it through a pump? Well, because we need hot gases at high pressure at the turbine. And so we use the pump to increase the pressure from low pressure to high pressure. So here at the exit of the pump, we get high pressure, but low temperature. But then again, we need high pressure, high temperature at the turbine inlet. So to fix the temperature part, we send it through a boiler. So this is how the entire thing works, right? Each device here does a certain job, and it gives you what you need, which is essentially converting heat to work. So steam power plants are all devices which operate in a cycle. So when you talk about a cycle, the starting and the ending point is exactly the same, which means that the change in any property within a cycle is going to be zero, or En minus E out is going to be zero. I can say the same for enthalpy, volume, any property, right? In a cycle, the starting and the ending point are exactly the same. So when I talk about this in terms of the energy for the overall system, I can say that the different ways in which the energy enters the system, such as heat input in boiler or work input in a pump, should be exactly equal to the way the energy exits from the system, such as the power output or the work output in the turbine, plus the heat output or the heat rejected in the condenser. So this is essentially what we can get from it. Or another way of seeing that is the net heat input should be equal to the net work output. Okay, and this is what we get by combining, by dealing with uh, the power plant or any system at the overall cycle level. We'll talk about how we can make use of this, and we'll solve problems related to this in the next few classes. But this is roughly the whole purpose of talking about different steady state steady flow systems, right? Steam power plant is of course one application where we made use of two heat exchangers, a pump and a turbine. There are a lot of other applications. So for example, if you're dealing with an air conditioning application, okay, we have to we make use of a compressor, two heat exchangers, a condenser and an evaporator, and also a throttling valve. Okay. So again, why do we do that? Well, each of them achieve a certain job. We'll talk about them in chapter 5. Okay, so that's it from me now. I'll be uploading one more lecture on this in an hour. So you got to make sure that you complete, you go through all of these lectures because these are part of the major exam. All right. Thank you and see you again.